After studying this module, you shall be able to know what does the term breath alcohol testing devices mean, what is the need for such device, that also you shall be able to know, and you will know how such devices came into existence. We shall also look what are the various breath alcohol testing devices and also about the common sources of error which are there in such devices, and they may give you wrong inference. So, you have to be cautious and knowing all these things. So, let us go into the detailed study. We often hear and read about cases of road accidents where the drivers are charged with drunken driving, and usually a news report claims the driver's breath alcohol concentration, which is abbreviated as BAC, is found to be much higher than the permissible BAC level. But how do the cops determine whether the suspected driver is actually drunk or not? The answer is breath alcohol testing devices. Drivers who can pass sobriety tests, that is they can walk in a line or can touch their noses, still might be violating the permissible level of BAC and may be a hazard on the road. So, the latest technology which is being employed by the officials to measure alcohol levels in the blood of drivers is the measurement of BAC level, and that is done by the breath alcohol testing devices. So, with this background, dear students, let us study more about this in detail with the help of graphics and visuals.
Of breath alcohol testing devices. Alcohol intoxication can be legally defined by the BAC, but the idea of drawing blood from the vein of a driver of a vehicle so as to determine whether he is drunk or not doesn't seem to be practical. Urine tests too proved to be equally impractical as blood sampling. This gave rise to a need of such an instrument which could overcome this problem. Breath alcohol testing devices serve a very useful purpose as they use a sample which is easily obtainable along with a rapid and accurate result. Origin and development. In 1927, Emil Bogen took the initiative and determined that the alcohol content of 2 liters of expired air was a little more than that in 1 ml of urine. By collecting this air in a football bladder and then testing it for alcohol traces. However, the very first research which gave the possibility of using breath as a sample for testing BAC was made by Anstey in 1874, who gave the observation that minute amounts of alcohol were present in exhaled air. Further, in 1927, W. D. McNally, a Chicago chemist, invented a breathalyzer where breath sample is allowed to pass through chemicals in aqueous medium, leading to a change in their color. However, the first practical roadside breath testing device intended for use by the police was developed by Professor Rolla N. Hager in 1931 and was named as drunkometer. This device collects a sample of breath and pumps it into an acidified solution of KMNO4. The alcohol present in the breath would change the color of the solution. The greater the extent of change of color, the more will be the breath alcohol concentration. Many studies and researches have been made time to time in this field, but it is widely accepted that Dr. Robert Borkenstein was the first to create a device that was able to determine the BAC by using a breath sample. Since 1954, the breathalyzer has undergone several modifications, but basic principle and design of the instrument remain the same. Principle of testing: alcohol is absorbed from mouth, stomach, and intestines and finally goes into the bloodstream. As soon as the blood reaches the lungs, a part of alcohol moves to the alveoli of the lungs because alcohol is volatile. BAC is in proportion to the alcohol concentration in the alveolar air, and the breath alcohol testing devices measure this alcohol in the alveolar air when exhaled. Instead of taking driver's blood sample to test his level of alcohol in blood, his breath could be analyzed on the spot and the officer can come to know as if there is a valid reason to arrest the driver or not. There is a direct relation between the alcohol concentration in blood to that in breath. The amount of alcohol contained in this 2100 ml of alveolar air is approximately equal to the amount that is present within 1 ml of blood. So, the breathalyzer measures the amount of alcohol present in 1 by 40 of 1 ml of blood, hence estimating concentration of alcohol in blood. Types of devices. These are of three major types, each of them based on different principle. Regardless of the type, each device has certain components, that is, a mouthpiece, a tube-like structure through which the suspect blows, and a chamber for sample where that blown air ultimately goes. First, we move on to breathalyzer. The device contains a sample collection system. Next, a reaction mixture contained in two glass vials. And third, a detector to measure the change in color of the reaction mixture as a result of the chemical reaction, instrumentation, and working. Breathalyzer is a device for collecting and measuring the alcohol content of alveolar air. When the valve is in take position, the subject is made to blow into a mouthpiece, which is coupled with a metal cylinder. As the subject blows, the pressure of the exhaled alveolar breath raises the piston to a height so that it exposes the two vent holes near the top of a heated cylinder and covers them, trapping the last portion of the air into the cylinder. The amount of air collected in this manner is 52.5 milliliters, which is 1 by 40 of 2100 ml, as the amount of air contained in this 2100 ml of alveolar air is approximately equal to the amount that is present within 1 ml of blood. So, the breathalyzer measures the amount of alcohol present in 1 by 40 of a milliliter of blood. When the valve is placed at the analyzed position, the piston begins to drop, resulting in the trapped alveolar air sample to pass into a glass ampule that contains 3 milliliters of 0.025% potassium dichromate and 0.025% silver nitrate in sulfuric acid and water. Let us try to understand the chemistry behind the breathalyzer testing. The alcohol present in the breath readily dissolves in potassium dichromate and gets oxidized to acetic acid. In this reaction, as the dichromate ion changes to chromium ion, the color of the solution changes from orange to green. The intensity of the change in color is in proportion to the quantity of alcohol in exhaled air. For determining the quantity of alcohol present in that air, the reacted mixture in the vial is made to compare with the unreacted mixture present in the system of photocell, which generates an electric current that makes the needle of the meter to deflect from its resting place. During this process of oxidation, the dichromate solution gets destroyed. It is the extent of this destruction which is measured by the breathalyzer, and the BAC is determined. Chemical equation depicts the changes that take place in the ampule. From the chemical equation, it can easily be deduced that there are 2 moles of potassium dichromate combines with 3 moles of ethanol. Hence, the amount of dichromate utilized indirectly determines the amount of alcohol that was present in the sample. AgNO3 catalyzes the rate of this reaction and does not undergo any change. Potassium dichromate is an orange color compound which absorbs visible light in the wavelength region of 420 nanometers. As the reaction progresses, the concentration of potassium dichromate starts decreasing, which in turn affects its absorbance. The breathalyzer thus indirectly determines the BAC by measuring the amount of light that is absorbed by potassium dichromate prior to and after its reaction with alcohol. Intoxilyzer. This device works on the basic principle of infrared or IR spectroscopy, thus identifying the presence of alcohol on the basis of its vibrational frequencies. Instrumentation and working. The device contains a source of IR radiation like lamp generating IR beam. The IR beam is made to pass through the chamber containing sample and is then focused on a rotating filter wheel by the help of a lens. The spinning filter wheel contains several narrow filters which are specific for the wavelengths of those bonds that are present in ethanol. A photocell detects the light crossing each filter and convert it to an electrical pulse. This electrical pulse is then directed towards a microprocessor which makes the interpretation of this pulse for calculating the BAC on the basis of IR absorption. Now we move on to chemistry. The hydroxyl group on the molecule makes it an alcohol. There are 4 types of bonds in this molecule. carbon-carbon, carbon-hydrogen, carbon-oxygen, and oxygen-hydrogen. These chemical bonds are covalent in nature, which can stretch and bend. This stretching and bending of bonds plays a crucial role in detecting ethanol from a sample by IR spectroscopy. Molecules vibrate constantly, and on absorbing IR light, these vibrations change. These changes include the stretching and bending of different bonds. Each bond within a molecule absorbs a specific infrared radiation at different wavelengths. The absorbed wavelength helps to identify the substance as ethanol, and the amount of IR absorption helps in determining that how much ethanol is there. Next, we move on to alkosensor 3 or 4. Alkosensor 3 and 4 basically work on fuel cell technology. The fuel cell is made up of two electrodes of platinum with a layer of porous acid electrolyte material between them. As soon as the exhaled air containing alcohol passes through the fuel cell, the platinum oxidizes it to produce acetic acid, electrons, and protons. From the platinum electrode, the electrons flows through a wire which is connected to the platinum electrode from one side and an electrical current meter on the other side. The protons migrate through the lower part of this cell and combine with electrons and oxygen to form water molecule. The more the quantity of alcohol that gets oxidized, greater will be the electrical current that will flow. The electrical current is measured by a microprocessor, which then calculates the BAC. Common sources of error. Breath testers are temperature sensitive and may give false readings if not recalibrated or adjusted to account for surrounding or ambient temperature of air. The subject's body temperature is also important. Pattern of breathing can also significantly affect results of a breath test. Following are the common sources of error in different breath alcohol testing devices. First, non-specific analysis. One major drawback of traditional breath analyzers is their non-specificity. That is, the machine also identifies other substances which have similar reactivity or molecular structure to alcohol. Traditional breath analyzer uses a solution of potassium dichromate for detecting alcohol, but it is a strong oxidizer and ether functional groups can be oxidized by it, which may result into false positive readings. Similarly, in case of infrared-based breath analyzers, other groups, most commonly carboxylic acids and aromatic ring compounds, can also give similar absorbance readings. Now we move on to calibration. Calibration is a process of checking and adjusting the internal settings of a breath analyzer by comparing and adjusting its test results to a known alcohol standard. Many breath analyzers use sensors made above silicon oxide sensor for measuring the BAC. These sensors are a way ahead in their susceptibility for interfering substances and are prone to contamination substances other than breath alcohol. Such sensors thus require replacement or recalibration at regular intervals. Next is interfering compounds. There are some volatile natural compounds which may cause interference, like NHTSA revealed in its study that diabetics and dieters may have acetone levels in their blood even thousands of times higher in comparison to others. Acetone, on the other hand, is an interfering compound which may give false reading of ethanol to some breath testing machines. Fuel cell based systems are, however, non responsive to such substances. Homeostatic variables. Breath analyzers work on the basic assumption that 2100 is to 1 is the partition ratio in converting alcohol measured in the breath to estimate the BAC. But this assumed partition ratio may vary from 1300 to 1 to 3100 is to 1 or even more among different individuals and within a given individual over a period of time. Next, we move on to testing during absorptive phase. After the last consumption, alcohol absorption continues from 20 minutes when stomach is empty to about 2.5 hours on a full stomach. Absorption peak is generally obtained within an hour. During this initial phase of absorption, the alcohol is not distributed uniformly throughout the body. Once distributed uniformly, a state of equilibrium is achieved, which generally is followed by the phase of absorption. In other words, some parts of the body will have higher BAC than others. During this non-uniformity, BAC in arterial blood will be greater as compared to the venous blood. Mouth alcohol. Mouth alcohol is the most common source of error as it can give false high readings. Breath analyzer's system works on the assumption that the alcohol present in the breath sample counts for the alcohol intoxication, but there are a number of reasons due to which false readings could be obtained, like acid reflux or gastroesophageal reflux is a disease which can greatly exacerbate the problem of mouth alcohol. Next, we move on to forensic and technical problems inherent in breath alcohol analysis. Forensic and technical questions arising in the use of breath analysis include the presumption of uncomplicated obedience to Henry's law, difficulties in capturing alveolar air specimens, uncertainty of the exact values for the blood or breath ratio for alcohol, as well as the effects of temperature, of variations in the cellular composition of blood, and of ethanol absorption and distribution into the water of the tissues. However, it remains advisable that the offense of driving while under the influence of alcohol should be statutorily defined in terms of the concentration of ethanol found in the breath in jurisdictions employing breath analysis. Let us now go through a case study of collision between two cars which resulted in multiple trauma. This case deals with a serious accident involving two automobiles on May 16, 1998 at 10:12 p.m. A truck driver was driving his pickup truck towards the south direction, and at the same time, a man was driving his car towards the north. Car driver lost the control of his car and swerved in another lane and hit the pickup truck. The accident resulted in multiple traumas, broken bones, and permanent injuries to the pickup truck driver. The police arrived at the accident scene at 10:19 p.m. and noticed that the car driver was visibly intoxicated and exhibited alcoholic breath with glassy and bloodshot eyes. He exhibited a lack of coordination and had slurred speech. The police officer took him to an area hospital and a blood sample was drawn at 12:36 a.m. on May 17, 1998. His BAC was found to be 0.14%. Car driver claims that his last drink was at 9 p.m. and the blood drawn at 12:36 a.m., that is a time lapse of 3 hours and 36 minutes. Since he was expected to dissipate 0.02% of alcohol per hour, he would have dissipated 0.07% of alcohol from his blood. The crime laboratory determined his BAC to be 0.14% in his blood drawn at 2:36 am. Therefore, 0.07% alcohol dissipated from his blood needs to be added to 0.014%, the BAC found at the time of blood drawn, which results in a BAC of 0.21%. Based on the time of his last drink, his BAC can be calculated at various intervals, including his presence in the bar, as well as at the time of accident from his blood drawn. Since the car driver's weight is 180 pounds, one alcoholic drink was expected to give a BAC of 0.022%. To get a BAC of 0.21% prior to his last drink, he would have had to consume at least 9 to 10 drinks. This is reasonable because he was at the bar from 4 p.m. until the bar closed at 10 p.m. So it is realistic to think that in 5 hours he could have easily consumed 10 drinks. The car driver was severely intoxicated with the alcohol. BAC of 0.21% would result in disorientation, mental confusion, dizziness, lack of coordination, staggering, and slurred speech. Thus, the driver was clearly unfit to drive.
So dear students, let us summarize what we have learned in this module. We have learned that a breath analyzer is a device for measuring BAC from a breath sample, and this is very easier to obtain as compared to taking the blood sample or the urine sample of the suspect. Dr. Robert Brockenstein in 1912 to 2002 was the first to design a device that measures a subject's BAC based on the breath sample. So this also we had a brief look into the history. And then we also studied that there are three most important types of breath alcohol testing devices, namely breathalyzer, intoxilyzer and alcosensor, and each working on different principles. We also studied that there are a number of factors like calibration, interfering compounds, etc., which could act as a source of error in these devices when we are using them. Forensic and technical problems inherent in breath alcohol analysis also we studied, and you should be cautious about to take care of these problems so that you are not committing any error while doing such tests. And we also studied a case study. Thank you.